It is a great pleasure to have with us virtually Sotiria Fotopoulou from the beautiful, picturesque Bristol. And Sotiria actually did her undergraduate degree in physics and her master's as well at the University of Athens. And then she moved to Germany, to Garching actually, to the Technical University of Munich, where she did her PhD in 2012. And then she moved to Geneva for a few years as a postdoc, and then from there to Durham, Northern England, for a few more years. I believe funded by the Swiss somehow, which is even better. You get a Swiss salary while living in Northern England. And then almost a year ago, she obtained a prestigious Vice Chancellor's Fellowship from the University of Bristol, where she has moved. Throughout her career, Sotiria has been working on various programs related to active galactic nuclei, from her thesis where she worked with Mara Salvato and Gunther Hasinger since today, and she's going to talk to us about machine learning methods for AGN identification. Thank you very much, Maria.
Thank you, Vasily. Thank you very much for having me. It's really a pleasure, and what a shame to not be able to visit you in Crete in person. But hopefully we will arrange that quite soon in the future. So yeah, today I would like to tell you all about identifying AGN with machine learning methods, and it's something I've been working on for a few years now. It all started in Geneva, working with Stéphane Polteny, and now it carries on. And here I just want to highlight the current gang working on these kinds of things. And here in Bristol, I'm quite fortunate to have a decent size group of students working with me and colleagues, which is always a pleasure. So a lot of it is done anticipating Euclid, because I'm quite involved in Euclid since I moved to Geneva since 2013. And we are all very eager in having the best possible data set we can have out of this great satellite. So I mean, I'm preaching to the choir in this audience, but you all know how galaxies are made out of, and the basic recipe in order to have a galaxy would be obviously dark matter, gas and dust, lots of stars, and the most important component for what I'm looking into is a supermassive black hole, which is found in the center of most of galaxies. And it is going to have a very complex structure of gas and dust around it. And here is, of course, a zoom in of just a normal looking galaxy. In the center, it would have a black hole lurking, most of the times being inactive. And then, of course, we have the great first image of a black hole, or the base of a jet close to a black hole. So whenever this black hole is going to have active accretion going on, it will turn out to be what we call an active galactic nucleus. And this is going to have a disk, torus, and sometimes jet structure around it. And the orientation between this structure and the viewing angle of the observer is going to give rise to the different types of AGN. So AGN in general emit across the electromagnetic spectrum from radio to gamma rays, and they are observed at the end. So what comes to our telescope is a combination between the radiation coming from the central part of the AGN, from all of these different components, and the host galaxy. So in the case where the QSO, the AGN in the center outshines the rest of the galaxy, we have what we call a quasar or a QSO, and the spectral energy distribution will look something like this with a red line. While if we have also the superposition of the galaxy emission compared to the QSO, we will end up with what I call in the rest of this presentation an AGN, or a hybrid emission, where it's an infinite ratio between the two. It could be any ratio between the host galaxy and the QSO component, and this would make up of an AGN. So what is the role of AGN? Why do we even care about all of these things? There are few pieces of evidence coming from different directions that actually give significance in the presence of a supermassive black hole in the center of the galaxy. The first one was that these supermassive black holes are found dormant in pretty much most massive galaxies, if not all. And the fact that they are dormant, it means that somehow they managed to grow, right? So they must have passed through an active phase of accretion. The other pieces of evidence was the observationally, again, M sigma relationship, where M would be the mass of the bulge and the stellar velocity dispersion, and the mass of the black hole instead of the mass of the bulge will give rise to a reasonably tight relationship between the two. And there is theoretical evidence or theoretical ideas why this kind of relationship is expected. And of course, the reason would be that the energetics of the system of the black hole are enough, if released, are enough to shape the bulge of the galaxy, and that would be obviously proportional to the mass of the supermassive black hole. So this is the first theoretical sign of feedback and self-regulation, and then later on we have the observational confirmation, if you will, that this is somehow observed to be true in nature. On top of that, we have, of course, simulations. Whenever we try to simulate galaxy evolution in a computer, it has been shown many times that if you do not include some sort of energetic feedback, it is impossible to reproduce the galaxy luminosity function, the normal galaxy luminosity function. And I have here an example by Croton et al., and the dashed line would be the luminosity function of galaxies in the K band if there is no AGN feedback included in the simulation. And obviously this is in large disagreement with the observations that you have here with the points. And once the energetic feedback is turned on, then the luminosity function, lo and behold, agrees with observational data. The trick here is that the feedback currently in simulation is considered as an energetic budget. There is no real connection to the physics of the AGN. It's just an on-off signature. And the reason, of course, is that it's very difficult to simulate the actual physics of an AGN in cosmological volume hydrodynamical simulations. And all of that is, of course, subgrid for the current resolution. So all of these pieces of evidence point towards the idea that most galaxies have gone through an evolutionary phase of an AGN, which is exciting news for the AGN people, which makes AGN a lot more important than we might have originally thought. And of course, in order to make a complete model of galaxy evolution, in order to put the pieces together, we need to have a census of the AGN population. This is a very difficult problem. And the reason is that due to the structure of the AGN, due to the different components, and due to the intrinsic nature of these objects, it's very challenging to have a single criterion that is going to select all of the AGNs. And here I have just a Mendeley of different selection criteria, ranging from the radio to the X-rays to optical through emission lines or mid-infrared. And you see how we have developed through the years the different selection criteria and optimize them for particular populations of AGN. But if we go and examine the number density of AGN we retrieve from each given criterion, we end up with quite a different view, with the X-rays dominating the number density of AGN found, all the way to the gamma rays, where very few AGN are found to emit in the gamma rays. Now, this is not a complete picture. This is very challenging even to compare, in the sense that there are a lot of selection effects that go here. So the issue is that there are sensitivity effects that are not explored to detail, mostly due to technical challenges, but there are also physical issues. What I'm showing here as an example of comparing the different selection methods, this is a work we have done with Dave Alexander. We put in a proposal for a WIV science verification project, which was accepted. And the idea here is to try to explore even further the different selection uh, criteria that we have for AGN and explore in this particular case the obscure population of AGN. What I'm showing here, this is an example of Donley in 2012, the different selection criteria between IRAC and WISE and X-rays. And what you see if you have, if you apply those selection criteria to the sample we were examining for the proposal, which was drawn from the XXL survey, the XMMLSS in particular, the central part, you see that the number density of AGN we expect with the different selection criteria varies quite a lot, ranging from 100 AGN per square degree to 180. Or if we go for a much more conservative AGN selection criterion, we end up with less than 100 sources. You can compare that with the expectation from the X-rays that I show here. And this is, of course, a selection of the luminosity threshold we can also apply, and then we can go from the very faint sources all the way to the most luminous AGN we can detect in the X-rays. So my personal take in all of this business is that we can use machine learning to not bypass, but somehow create a comprehensive way of identifying AGN. And what I put here as a comparison would be a quite early work I did on this particular field, where I was able to select 107 AGN or quasars per square degree for the same sample. So the expectation for Euclid is that if we believe these numbers are roughly correct, is that we're going to have in the 15,000 square degrees, we're going to observe something like at least 3 million AGN. So the AGN science is ramping up with the next generation telescopes, and this is very exciting. And the question is, can we get them all? Can we find all of the AGNs that are out there? Just to show you a little bit further, to scare you even more, if I haven't done so already, that the selection criteria do not necessarily pick up the same population of sources, even if we look only at the infrared selection criteria, for example, and we make the comparison between the Stern selection criteria, the Donley 2012, and the WISE selection criteria of Stern 2012. And you can see that even though there is a very large overlap, of course, in the middle, there are sources that are picked up only by individual selection criteria. And the same is true if you make a higher selection threshold for the signal to noise ratio. So you end up from 1,000 sources that would exist in the entire sample to 350 that would be selected by all selection criteria, which is just a third of the sample. So if we compare to the X-rays, on the other hand, and we have the Donley and the Stern 2005, we end up with 400 X-ray sources that have not been identified from the infrared. And the same would be true, of course, with the Stern 2012 selection criterion. So moving on the machine learning bit that I will tell you all the details in the rest of the talk, we have an additional 100 sources that can be identified from the colors of AGN that have not been identified from the infrared alone or from the X-rays alone. So this is somehow good news, but it seems that we are not quite solving yet the problem. We do have an overlap with many of the selection criteria, but we do not identify all of them just yet. The point is that we want to eventually go from the static view of the AGN, of the geometrical view of the unified model, where it would, of course, it's there, of course, it sets the stage of which kind of AGN we are going to observe. But we do know now that there is quite a dynamical process in an AGN. There is a lot of winds, there is a lot of self-regulation, which leads to evolution. And on top of that, we have the obscuring host galaxy, which could be an extra obscurer. And then the different kinds of AGN we are going to pick up with the different selection criteria are going to link eventually to the different physics that we have for the AGNs, where the obscuration is not simply a matter of orientation anymore, but it could be linked to the evolutionary stage of the AGN. And of course, the future is very bright. We want to be able to use to the most all of the data sets that are coming in the next 5 to 10 years. And I like to call that the dawn of big data. We don't really have big data in astronomy just yet. But we are actually looking for needles in the haystack, especially if you think about objects like AGN or quasars. These are going to be millions compared to the billions or tens of billions of sources we are going to have with Euclid and LSST. And I like to highlight here that, of course, SKA is going to be the most technologically amazing challenge ever, where they're going to get 160 terabytes per second in their detectors. But we have to keep in mind that both radio and X-rays that we're going to have with eROSITA will provide only a few millions of detections. We still need to be able to mine all of the data that we're going to have from Euclid and LSST, where it's going to be in the billions. Now let's move into source classification, and I will take you down the historical way of doing things to begin with, right? If we go back to the very first question that astronomers have pondered for hundreds of years, is it a star or is it a galaxy? If I would give you just an image of the sky, just like that, this is from the Subaru telescope, and I would ask the question, if this source here on the top, is it a star or is it a galaxy? I don't think you could tell me with very high confidence. Obviously, for this guy down here, you see the beautiful spirals. For this guy here, this is a very nice elliptical. This we can say immediately that these are galaxies. But the dots in the background is very challenging. So what people have done is to develop methods to identify these kinds of sources. And one of them would be, of course, the surface brightness, where we can see that as a function of magnitude, there is this sliver of population that seems to be different. And these would be what we call point sources, but not necessarily stars. We cannot say with certainty that they are stars. We can say from the geometry that they are point sources, while these guys would be extended sources, and most of the times we're going to be galaxies. Everything else down here would be a fake detection, like a cosmic ray or something like that. So the standard way of finding this kind of point-like sources would be, of course, with the source extractor, which I'm sure many of you have used. It's one of the most widely used pieces of software in astronomy. And there is a parameter there called stellarity, or class star, or however you want to call it, that will give you the point likeness of a source. It's very interesting to me, and I'm not quite sure how many people are aware of that this class star is given by a neural network that was trained in 1990s, when the extractor was first published, and it was trained on simulated images of stars, and they were in the B band. So what you see here is how the stellarity would work. It goes from 0 to 1, 1 being stellar, 0 being a non-stellar or point-like, and then you see it has a variation as a function of magnitude. As you would expect, quite a lot of the point-like sources tend to be the brightest ones. Now, naturally, this is going to break down eventually. It's not possible that the neural network trained in the 90s will be able to give a point likeness for all future observatories. And to be honest, it's quite impressive that it has lasted that long. And here I have two examples of two works by Desai 2012 and Sumanak 2015, where they describe that the stellarity really does not work at all when one looks at DES images, for example, and DICAM images. And this is something I have experienced as well. And they propose a different kind of classification criteria to find point sources. But is it really a star? Just because it is a point source doesn't mean that it has to be a star necessarily. And what I show here is a plot I have made. This is a plot you will see again and again for the rest of this talk. This is a color plot, Y minus W1 and G minus J. And I have the entire population of kids DR3. And I have as a color bar the class star from a source extractor. And the darker means point light, right? So all of these guys down here that are quite dark are stars, as we would expect them to be from their colors. But all of these guys here, this dark cloud, these are all of the quasars. And they are called point-like, right? So clearly a morphological classification not only does not give us the correct physics of the source, but eventually has to be trained on the specific images we're looking at. And this is another example of the gamma survey where they combined, as they did very nicely, the morphological classification of the PSF and the colors in order to split the stars from the galaxies. Now, the machine learning bit, I'm not quite sure what is the level of expertise in the audience of the machine learning. So if you're experts, please bear with me. Just a little bit of overview of how the machine learning works. So the idea here is that we are trying to make a mapping between an input and an output. And in this case, the input would be colors, anything we get from our broadband photometry, and the output could be the class star or not star, referring to the previous example. So supervised learning can be trained to make this mapping for us. And usually it boils down to the idea of either having a network or a decision tree, and a complex creation of either the two eventually leads to all of the sophisticated models that exist in the market today, like convolutional neural networks, random forest, GANs, and so on and so forth. But this means that we have a label that we trust and a label that we try to reproduce. So this could be the case for stars, but as I have shown you already, this is incredibly challenging for the AGN part. On the other hand, we have unsupervised learning, where for whatever reason we don't have or we don't want to use a label training set. So what we do in this case is pretty much clustering analysis, which in astronomy we know quite well. And there are different ways of doing that. It could be distance-based or density-based, or it could be also through a neural network. And I will come into the details of the DBScan a bit later on. So the application of the machine learning, the supervised machine learning for me, has been to identify the optimal photometric redshift library setup for any given galaxy population. And this is an extension of the work of Mara Salvato in the Cosmos fields. And the hope here was to do it in a very automatic way that is applicable for all future surveys. So the idea here is we try to extract the different kinds of galaxy classes, but also try to identify the stars. So the sample I used for this work was a spectroscopic sample drawn from the overlap of SDSS and the VISTA surveys, which turns out to be about 200 square degrees. And I managed to gather 50,000 spectra from a variety of spectroscopic surveys, most notably, of course, the SDSS. So the idea behind the CPZ, the classification-aided photometric redshift estimation, is to have a monolithic approach for an extragalactic field in order to get optimal photometric redshift. And the first step would be, of course, of gathering the data, homogenizing all of the different filters, making sure everything is corresponding to each other correctly. And then we move on to the machine learning classification stage, where in this particular application, I'm using random forest. And the labels come from my training sample, where I have the best fit SED for photometric redshift. And the idea here is that we can define three distinct classifiers. One that would tell us if a source is a star or not. The second classifier will tell us which photometric redshift library is the optimal one to use. And the third one will tell us if it is a photometric redshift outlier. And once we have all of our classifications, we can select the different kinds of probability thresholds we want to have from each of our classifiers. And we go through the consolidation phase, where we get to reject outliers or stars or select the threshold that is optimal for our given science, and then we end with the optimal final sample for redshift. Just a very quick run through the different classifiers. What I've had in this paper, I tested different kinds of selections of photometry. This is combinations of broadband filters ranging from the U band to the K, or having the infrared or the ultraviolet selection. And you see that, of course, according to the filters you consider, you have a different amount of sources, but you also have different accuracy of the classifier. But the star classifier tends to be quite accurate and very, very well distinguishing between the stars and the galaxies, just because they have so different colors compared to the galaxy population. So what I'm using here is an input of about 200 attributes. I'm taking every color combination between these filters. And here I'm just showing a plot that I actually learned from the random forest as being the most informative one. And this is the one I'm using for the rest of the talk. And you can see that the stars are the black dots here at the bottom, and they're quite distinct compared to the galaxy population with the gray points. And as you can, another way to see that the classification is working very well is, of course, to see the confusion matrix, where you have the star is really classified as a star, where the galaxy is not. So doing the same work on the galaxy side now, we try to split between the different galaxy classes. And of course, it's a lot more challenging this time, because the colors are not as distinct from each other. And you also have the redshift effect that is blurring the colors, if you will. So the idea here is ranging from passive to star forming all the way to quasars, and having the very messy class of AGN. And trying to figure out which configuration would give us the optimal photometric redshift and the optimal classification. And for this paper, what I chose as the optimal was the best outlier. I wanted to have the least outliers out of all of my photometric redshift. So the decision was that we want to have pure classes. We don't want to mix the different galaxy populations, and we want to assign the proper priors on the luminosities for the QSO using the templates that have been constructed for the Cosmos survey. And here are the color plots for this particular classification. This is again the same plot as I showed before. The stars would be down here. And you see how the passive galaxies, the star forming and the starburst are all over the place, while the QSO are very well isolated in this corner of the plot. So the QSO themselves are very different compared to galaxies, as we can see also in the confusion matrix. So we're very successful in finding QSO when we use brown-band photometric colors, while at AGN, that would correspond in this column of the confusion matrix, are getting confused a lot with star-forming galaxies. And this is quite expected, because they actually do look like star-forming and star-bed galaxies, of course, because they're a ratio between these galaxies and the quasars. And this is another view. If you're used to seeing the BZK diagram, this would be the analog. And this would be the WISE plot. And you can see here the blue color represents the quasars. And you can see how well they're isolated from the WISE plot, and also from the color coming from the random forest classification. So this was all good news for the quasars, and it means we can sort of industrialize photometric redshift estimation in an optimal way. And this is what we have done for the XXL survey, where now we have 10 million sources, and it would have been impossible to go and visualize each one of them and see by eye if they look point-like or not. But now we can do that in an automatic way. You can see again the quasars are very well isolated, the stars as well. Very interestingly, the passive galaxies are quite nicely isolated, and of course, star-forming, starburst, and AGN are quite messy by nature, I would say. And now this is a different way of seeing the same success of the AGN classifier, if you will. So this is the WISE plot, W1 minus W2, and here on the x-axis I have G minus Z. And here I'm showing 4 different ways of identifying AGN, and they're not all of them communicating to each other. So what do I mean by that? The WISE plot or the WISE selection of CERN 2012 would classify as quasar sources that are above this line. So everything that is above and the top of this plot. The random forest classifier is here shown with a color. One would be the passive galaxy and the quasar would be the darkest red. So all of the stuff I classify as quasars are also found by the WISE selection criterion. The sources that have a color are sources that have the X-ray emission from the XXL survey. This is the XXL 1000 sample. This is the brightest, 1000 brightest sources in the XXL survey. So you see, we would have imagined that all of the X-ray sources would be AGN, most of them, but you see that the classifier from the optical color shows that quite a lot of them are quasars, few are AGN, some are star forming, but you also have quite a few that are classified as passive, which are the darkest colors, and the passive ones do fall below the WISE selection criteria, are where you would expect the passive population to be. Now the fourth approach is also for the X-rays. So the X-rays are never part of the classification scheme. The random forest has never seen X-rays during the training phase, but it has also never seen broad line emissions from spectra. The spectra are never part of the training. And here I put with a square all of the sources that seem to have broad lines in their optical spectra. And lo and behold, all of the sources are above the WISE line, the WISE selection criterion, but they're also the sources that identify as quasars with the random forest. So this plot gives me quite a lot of confidence that the classification is working pretty well, at least for the quasar population. Now, moving on to the unsupervised bit, as I've motivated at the very beginning, identifying an AGN is a very challenging task to do. While a quasar, because it is so bright and so different, it could be a lot easier. So the idea here is, let's ignore for the moment the labels, either from the SED fitting or from spectroscopy, and try to cluster our sample and identify the different population of sources, while knowing that we do have some labels for them. So the idea here is that we are using density-based spatial clustering, which is the method is called DBSCAN. And the idea is that you set a radius where you search for neighbors, and you also set the minimum number of neighbors you expect to have. And by having these two numbers, you scan through the entire catalog, and every time a point has the minimum number of neighbors within a given radius is called a core point. And then by doing so, you connect core points to each other until you reach the edge where you are a neighbor to a core point, but you're not a core point yourself, and this defines the border of the cluster. And then, of course, you have sources that are outliers. They are not part of a cluster. They're not a core point. They're not a border point. So these would be outliers. So in this cartoon, we would have identified 2 clusters and 3 outliers. So the idea was to start with this method, and I asked Crispin to go and have a look at that, and he said, well, this sounds nice, but I do have a much better method than that. This is the hierarchical version of DBSCAN, where instead of having a fixed radius, what you do is you gradually increase the radius, and now you only have as a parameter to play with the minimum cluster size. And this is, of course, equivalent to running DBSCAN for every value of the radius. I don't think I have the time to go in the details of how the method works, but I would welcome you to go and have a look at the documentation of the code. It's very well documented on how everything works. Just briefly, we scan and we enlarge the radius until all of the neighbors are found. A minimum spanning tree is constructed through that, and all of the points are linked. And then this is converted into a dendrogram, and then this dendrogram is collapsed in a more compact version, and then the thresholds where the clusters should be are defined from this compact dendrogram. Now we applied this method exactly on the same data set as I showed you before, the CPZ sample. And the idea here was that we didn't have labels for all of the sources, which was fine. And what we do is we say if a source doesn't have a label from the spectroscopic analysis, we looked at its redshift and we found 42 sources that have very small redshift. So we assumed that these sources are stars. They were just not labeled as such. While the rest of the sources that didn't have a label, we claim that they were just boring enough to not have a special label, so they must be galaxies. It's not crucial for what we're discussing later on, but this will give us an idea of what kind of sources we are looking at the unsupervised classification. So the idea here is, again, we start from the entire sample, we create all different color combinations, and then we go into the fuzzy box of the machine learning part with a lot of stuff happening, and I will expand on this in the next slide. And then we build 3 models, one for stars, one for galaxies, and one for quasars. And here, this is the location where we can get new data that can be classified that have not been part of the training. And then, of course, we always have the consolidation phase. So expanding this little box where the devil is always in the details, you go from your observed colors, you do all of the pre-processing that needs to be done for the machine learning bit. And then the idea is you start to explore different combinations of attributes. The point is that random forest that I used previously has no issue in dealing with 200 attributes as input, while unsupervised learning methods like HTV-scan cannot deal with such a high number of attributes. So we found that we had to do a dimensionality reduction and a careful selection of the features, which is what they call in data science feature engineering. So we ended up doing principal component analysis to different dimensions to figure out which one was the best one. And of course, you do the grid search to find the optimal parameter for your machine learning exploration and go through all of the metrics and choose the optimal model for each of the 3 models. So we end up having 3 distinct models for stars, galaxies, and QSOs. And this is how it looks like in parameter space now. So what I'm showing on the top is finding QSO in PCA space. The blue bit, the blue clump is the QSOs we identified because we know their spectroscopic labels. But you can appreciate that we have 3 distinct clumps. They're quite separated from each other. And this would be the labeling after the consolidation phase, after everything is done, where the QSOs would be down here, the galaxies would be in the middle, and the stars would be the black dots. So going through this feature engineering and through this PCA dimensionality reduction, we are actually able to identify these 3 distinct clumps quite successfully. And here I have the metrics of the classifier for the 3 classifiers as a function of magnitude on the top and as redshift for the bottom. And you can appreciate that the accuracy, which is the green line, is pretty stable across magnitudes and redshifts. So it was great news for us. So a brief comparison between the labeled version and the supervised version and the unsupervised version we would have here on the top, where you have the SDSS labels, the spectroscopic labels from the automatic pipeline, and you see there is a large overlap between the quasar and the galaxy population. And we know this is not correct because this was the version that came out from the Paris 2018, where it was a vetoed version of the quasar catalog, a much higher fidelity catalog. So if one takes the labels at face value from SDSS and does random forest classification, for example, you will end up with a result that was published for kids tier 3, where you do have, again, the mirroring of your spectroscopic sample because this is what you train on. While if you do unsupervised learning, you end up with something more pure. You might admittedly miss a few of your quasars that would fall on this cloud for whatever reason, but you are able to have a purer sample of quasars, galaxies, and stars. And I don't have the time to go into the details. We also identify outliers, sources that we're not confident that belong in either of those classes. So I think I will possibly skip the details of the outliers, but we can come back to it later on if you want. Another thing we are doing with machine learning is not identifying the AGN the traditional way, if you will, which is what I've discussed up to now. The idea here is to use the machine learning as a tool to speed up the SED decomposition between the host galaxy and the AGN component. And this is a work we started with Mike Walmsley, who is a PhD student in Oxford, and a group of other people that you have listed here. And that was part of the project we started at the Kavli Summer Program last summer. And the idea here is having a very fast machine that will give us the fraction of an AGN within any given SED. And here I have examples of SED decomposition from Buongiorno 2012, where the black is the entire galaxy or the observed data set, and then the galaxy would be the blue line, and the AGN would be the blue line, and the galaxy would be the pink line. So if you have done this kind of business in the past, you know this is a very time-consuming problem, and it can take from 10 minutes to an hour to fit just one source. So if we have a billion sources, like we're going to have with Euclid, this would require 100 to 600 million CPU hours. So it's absolutely infeasible. So the idea would be instead to emulate the model space and do forward modeling on the fly. And this would mean that we map the parameters of the model to the expected broadband photometry. And this is what Mike has done. So what I'm showing here is just preliminary results, of course, and we're still working on it. What Mike did was to take 20 million galaxy SEDs from FSPS, and he introduced the AGN disk model because it was only the torus model that was available when we started the whole work. And the idea is we create a deep neural network to map the physical parameters to the observed photometry. And this neural network is very useful during this forward modeling, because this is now a differentiable object within TensorFlow probability, and this makes the gradient descent or whatever optimization algorithm you're using quite fast. So using the neural network for the likelihood calculation, we have achieved a dramatic speed up of about 600 to 3,000 times, depending on obviously the photometry that is available, which means now we can fit about 100 galaxies per minute on an average GPU. And here are results from simulated data. And you can see what kind of physical parameters we are able to extract. And that will be, of course, stellar mass tends to be the easier one. We are able to get parameters for the AGN, like the disk scale or the extinction and the torus. Not when the torus is prominent, as you would expect. These things are quite fuzzy down there. And imagine that you can appreciate the star formation is a lot more challenging if we don't have far infrared data, and this is the case for this data set, and this is quite realistic. It's very difficult to get concrete star formation rate from this kind of photometric data set. So this brings me to the end. For me, the dawn of big data is upon us in astronomy, and it is very exciting for many of us. Next generation telescopes are going to provide a lot of challenges and hopefully a lot of answers for galaxy evolution problems. And machine learning applications are new ways to solve very old problems. And of course, they can be used for exploratory analysis, but the challenge here is to use it with care, never use it as a black box, and obviously respect the limitations of the model you're creating. And obviously the holy grail is making the link between the models we're creating with all of this complex machinery and explainability, and bringing back everything to the physical parameter space. And I think that's all I have to say today. Thank you.
Okay, thank you very much, Sotiria. This was very interesting. If there are some people who have a question to ask, you may raise your hand and I'll try to see it. I call your name. Let's see. If there isn't anyone for them. Oh, Andrea, go ahead.
Hello, Sotiria. That was a very interesting work. Very exciting results. So I have two questions. The first question is for the first part of your talk. So you mostly focused on QSOs. Have you tried to expand this to other types of AGN, like safer AGNs or liners, for example, this type of thing, or or it's not good enough?
So this is something we are doing right now. I have a student from computer science. Mm-hmm. So we are trying to identify AGN as outliers. So the point is that the AGN are going to fall on the galaxy cloud, right? Because they don't look distinct enough. So what we are trying these days actually is to try to learn the galaxy part very well, and then presenting this classifier with an AGN, it will tell us that it doesn't look good enough. That will be an outlier for this particular analysis. So this is something I'm very excited about, and hopefully I will tell you in a couple of months how good or bad we are with this. It's very challenging, right? Because usually the signatures, let's say for a liner, could be that you see it only with the very high resolution spectroscopy. Yep. Which for Euclid is not going to be the case. So one of the questions we try to answer is how far can we go with broadband photometry? And how much do we care for Euclid specifically?
Exactly. So this could be equivalent to looking at the chi-square of a feed and putting up the bad feed.
Yeah.
Okay. So this is very interesting. So I'm looking forward to this to these results. The second question, which is somewhat related, is in the second part of your talk, you discussed about doing SCD-based AGN decomposition, and so have you looked into including additional information like radio or X-ray information that will help further to separate the AGN from the star-forming component? That's one thing. Or possibly adding spectral information, like for example, the fold would have maximum of the spectral lines or line ratios. So in addition to the photometric data, you can expand to other non-photometric space.
Yeah, so one of the limitations you have with the machine learning business is it's not possible to deal well with missing data.
Sure.
The challenge of radio and X-rays is that there are so few sources compared to the bulk of the population that you find in the optical and the infrared, that it actually, at a certain stage is a hindrance on your machine learning models, right? Because Euclid will have 10 billion sources, while Rosetta will have a couple of million.
Yep.
So we can try to use it in a indirect way, if you will. We can define our training set based on sources that we know have X-rays, and try to find similar objects. But I would be very skeptical in including the X-rays directly into the machine learning bit. Or you just work on an X-ray sample. Of course, that can be done. That's
right,
clear.
Exactly. Yeah. Although there is the additional information that if there is something that doesn't have X-rays, or has not detected X-rays, it's useful information.
Yes, absolutely. But the depth of the X-rays, or Rosetta specifically, over the entire sky, I think is not well matched to the depth of Euclid.
Yeah, of course.
Okay, thank you, Andrea. If there is not someone else, I would like to ask a question. Sotiria, you mentioned that the major motivation for this work is Euclid, right? Which will give you billions of sources. But that you will compare with, you will create a band merge catalog with the WISE, right? You need to compare with all sky or nearly all sky surveys, right? Mm-hmm. So my question is, I was looking at your the last, for example where you show how well you can estimate, say, stellar mass, and then you talk about dust. But I presume you will mostly use the first two bands of Ys, right? Because then the PSF becomes very large.
Yeah.
So whatever estimate you get is from the assumed optical extinction, right? So I was a bit surprised that you can that the method works so well, or at least it looks it just looking at the correlation, right? Because of the fact that if you have an AGN, this is sort of like it will affect the stellar mass estimate. I mean, it's a cyclic problem, right?
Definitely,
it's difficult to estimate. So I was impressed that it seems that the method works well and it can estimate the stellar mass and the dust at the same time.
Well,
while you have an AGN in it, right? So
these are the best case scenario. They're simulated data, right? So
okay.
we will apply this in a more realistic data set where I expect everything will be a lot worse. But the challenge is that you don't really have the truth value on a realistic data set or in a very large data set, right? So you start from simulated data, you convince yourself it is at least working there, and then you move on to real data and play with that. But I definitely agree with you. This is a cyclic problem. There is a lot of degeneracies all over the place. And it's not that you are solving the issue with the machine learning, is that you're only speeding up the computation. So the same challenges you had before with your chi-square, you're going to have exactly the same issues when you substitute the
and in real life, when say that Euclid flies and all instruments are working and so on and so forth, what will you use as your sort of like band merge catalog, right? What sort of, how many photometric points do you expect to have for the bulk of the data?
Yeah, so it is, yeah. It is an issue. So the point is, what I'm doing within Euclid is connected to the core science, because I'm part of the photometric redshift group, and I'm doing the classification for that. And the idea is we are going to provide a catalog for the weak lensing analysis, which means we need to identify all of the stars and all of the sources that will have a programmatic photometric redshift, which is going to be all of the AGNs and the quasars, right? So for me, there is good motivation from that respect, meaning I can use all of the proprietary and internal data we're going to have for that purpose. So for Euclid officially right now, we're going to have 7 bands, maybe 8, U, G, R, I, Z, Y, J, H, 7 bands. For the WISE bands, it's something I have been trying to motivate to have it in an official way within the collaboration, but the challenge within Euclid is that if you want something to exist in the official pipeline, if you need to motivate, it's part of the requirements to achieve the requirements for the core science. The challenge of Euclid is that the WISE is that the PSF, as you said, is very large and it requires a lot of processing to match to the Euclid data set that is going to have a Hubble resolution. So it's a lot of extra work for people. So it's something to discuss. We'll see how it goes. But the real question is, how far can we go using only the Euclid dataset?
So you mentioned that you have 7 bands with Euclid.
Yes.
Because I thought it was only 4, but
Yeah. So Euclid itself is the V's band, which is RI and Z combined, which is not very useful for photometry, is what we use for morphology. And then you have YJH.
Right.
But we have agreements from the ground to have external data.
Oh, okay.
For UGRI. Yes, I'm sorry, I didn't clarify that. So the agreement is, again, only for the photometric redshift and classification, but not necessarily for the physical parameter estimation. This is something we're discussing currently within the collaboration, how we can make this happen.
Okay. Thank you very much. I don't know if is there anyone else who would like to ask a question? Thomas, since you joined from Germany, no, I'm just
Yeah. No, I was I was wondering if these algorithms are publicly available anywhere, or in a repository, or on GitHub.
Yeah,
Is it?
so the first part, the CPZ part, I haven't made this available because it was tailored for that particular dataset and it was a bit of a mess, let's face it. But the HDB scan one, we made this available a couple of weeks ago. So I think the fastest way is if you go to my website, I have a link there and you can find
Okay.
the whole code. So we made it as package-like as possible. So you just plug your catalog and you just go through the classification.
Yeah, I would be quite interested in these algorithms because we are trying to develop similar algorithms for CO sleds on extragalactic observations, and I would like to see how what is the structure of the algorithm, and because it's a new thing for me, and I would like to see it through. Yeah.
I'm happy to chat more if you have specific questions. To be honest, the algorithm itself is not as scary in the sense that the machine learning bit is very well documented and very well created. I mean, the machine learning or the data science community is very active for these things. The scary bit is everything you do around it. So the pre-processing, the selection of your data, your feature engineering, this is the where the meat is.
Yes. Okay. Sure. You should keep in touch and
yeah, definitely.
about that. Okay.
Okay. If there are no more questions, and I see no other hands raised, I would like to thank Sotiria on behalf of all of us for preparing this very interesting presentation, and we do look forward to have you in physical presence at some point in Crete in the near future, one of the summers down the road.
I hope so too, yes.
Okay. Thank you very much, everybody.
Thank you.